are recording at the same time. All right, so sodium bromide, it's a crystal. It would look like sodium chloride, I expect, and in terms of physically, but this is what a sodium chloride crystal looks like as well. And then what would happen is these things would go into water, and when you put this into water, what would happen is the ions would separate off, and then waters would come and surround those molecules. So those, I'm not those molecules, those ions, okay? They're not molecules here. They're just single element ions. And so, first off, they don't tell us which one's sodium and which one's bromine here, right? But it looks like, which one do you think this one is? 2 clues. Sodium. How do you know it's sodium? Positive. It's positively charged, right? How else, if you didn't have the charges, how would you know it's sodium? Look at the periodic table. So here's our sodium, here's our bromine. Be a great quiz question. Great final exam question. Because we're already past this stuff. So remember our sizes on the periodic table. Things get bigger as you go down the periodic table, right? Okay, so they get smaller as you go over to the right, so that might be a little bit confusing there. Although sodium, it's going to be sodium plus, right? So what's its electronic configuration? It's sodium plus. It has the electronic configuration of what was that? Neon, right? So essentially you're really comparing this, right? And bromine. Bromine minus, what's it have the electronic configuration of? Argon, right? Picks up an electron. Everybody wants to be a noble gas. So really, we're comparing these two. Okay, so which one's bigger? Yeah, krypton or bromine really is what we're comparing, right? But bromine versus sodium. But regardless, even if you got lost in us moving to the noble gas configuration there, bromine is farther down the periodic table. It's going to be bigger. You can pretty much count on anything farther down being bigger. I'm sure there may be exceptions to that, but that's the general rule I would use there because you're occupying a bigger shell, right? Okay, it's not the same shell with more protons in the nucleus. It's a bigger shell. Okay, anyway, we're going to surround these. And you'll notice they did this picture very nicely in terms of how they're surrounding these, right? If we drew a water molecule, and you guys did quite well on this in the quiz, in terms of the polarity. Remember, we've got polarity in a water molecule. The difference between oxygen and hydrogen for electronegativity is 1.4, I think. Okay, I'm not going to bring up the table, but it's 1.4, and so it goes this way. Right, I've got 2 arrows that are opposing each other in this direction. They're coming together, really, okay, but still they're opposing each other in this direction. But in this direction, they're going in the same direction, right? So water is polar. It has a dipole. So we could think about a partial negative charge up here and 2 partial positive charges down here. Okay, we have a positive side and a negative side. And if you look at the way they've drawn their molecules of water here, the negative oxygen is associated with this positively charged sodium ion. And over here, I keep going over here and going, gosh, it's not right. But over here, the partially positive hydrogens are associated with the negatively charged bromine ion. Okay, so there's a lot going on in that picture. All right, all I really want you to get out of that picture is, well, 2 things. I want you to be thinking about these spheres, right? Think about the things we've learned already, but also think about atoms as spheres. We're writing out these formulas. They're words, or they're letters, right? But they're these spheres that interact with each other. And when you have a molecule, they're the spheres that are attached to each other, okay, through covalent bonds. So think about those in that perspective. And then also think about when this dissolves in water, those ions break up. The spheres that make up my ionic crystal break up. So that was all conceptual. And so when we think about things dissolving in water, we talked about two types of equations that we are going to expand on when we talk about precipitation reactions. So here we have our sodium bromide that's up above, and that starts as a solid, and it dissolves into water, and it becomes, we can express that as sodium bromide aqueous, okay, and that would be our molecular equation. Or another way of expressing the same thing would be that those sodiums break away. So we make aqueous sodium ions and we make aqueous bromine ions. Bromide ions, I should say. And then this is going to be the ionic equation. Had a question there. Bromine is diatomic, but not as the ion. So that's a great question, okay? Bromine, chlorine, fluorine, iodine, all diatomic when they're elemental, when they're in their neutral form. But when they get electrons, right? Let's talk about that really quick. So iodine. Or let's do bromine, because that's the one we got on the screen, right? Bromine is going to have a Lewis dot structure that looks like this, right? Each bromine has 7 electrons it brings to the party. Okay, so 14 electrons total. We'll use 14, 2, 4, 6, 8, 10, 12, 14. We'll use 14. Why does it do that? Why isn't it separate bromines? A separate bromine would look like this. Why isn't it this as opposed to that when it's neutral? Yeah, you want to complete that outer shell. You want to follow the octet rule here. So for these ions, we can violate the octet by adding more when you get farther down, when you get down to bromine's level on the periodic table, but you can't have less. And so what we've got here is these each have by sharing these 2 electrons, they fulfill the octet rule. All right. But what if I take my bromine and I make it a minus, which means I'm giving it an extra electron? Like that. What about now? What do you see here? Yeah, we have a full octet already, so there's no reason for bromine to bond with another bromine, or anything else for that matter. Does that make sense? Okay, and when I talk about the ions, I should say bromide, right? They're bromide ions. Sodium bromide. And I hope I didn't say sodium bromide up there. I'm pretty sure I didn't. Okay, so we have those 2 types of equations, right? We have our molecular equation or our net ionic equation, not our ionic equation. It is a net ionic equation as well, but we'll talk specifically about what a net ionic equation is in a little bit. All right, and what we're working up to today is we're going to talk about the solubility of compounds, and we're going to use this table over and over again. And I'll send you an email on this, whether you need to memorize this table or not. We're just going to use it today, okay, when we talk about things. But so we can think about when we bring together these ions. So far, I've talked about things that are very soluble in water, all right? So what you have when you think about that ionic crystal Okay, we have ionic interactions which are very strong between the sodiums and the bromides. Okay, the sodiums and bromides have very strong they have ionic interactions. Ionic interactions are very strong, but when you put them in water, water interactions are also very strong. All right, so we have a tug of war between these interactions and these interactions. And we have another thing going on, which is called entropy, which we will cover later in the course. But essentially, you have a tug of war between these interactions and these interactions, and which is going to win. Okay, that's what essentially what happens. And for some things, for some particular ionic compounds, the water wins, right? And so the ions come apart and things are more stable when ions are surrounded by water molecules. And for some ionic compounds, the crystal wins and it won't dissolve in water. Okay, the ions don't separate in water. And so that's what's going on with this solubility table. And this is the table we will use. There are more things in this, but this is kind of the basic table we'll use for this. And like I said, I don't know whether you're going to memorize this or not. I need to talk to my colleagues and see what they're doing, and then we will match the other classes. But for now, for today, we'll just use it, and don't go out of here and start memorizing it. I'll send it in my email today once I talk to the other professors. All right, so what we have, though, is these compounds. If we read this table, we're going to walk through it. These compounds up here are almost always stable. So anything that contains these is going to be soluble. So you just look at it, and if I have a lithium, a sodium, a potassium, etc., what's etc.? Whoops. What's etc. going to be on the periodic table up here? They're lazy, but they were lazy, but maybe in a pedagogical way or instructive kind of way. Lithium, sodium, potassium, what's etc. going to be? You don't need to know the name, but you can make up a name. Rubidium, you guys are dead today. Cesium, francium, okay? You didn't need to know the names, but because there are people. But etc. means everything in that column, okay? And because it didn't take many electrons for them to actually increase that, I'm assuming that they were trying to teach a lesson for etc. there, okay? Ammonium, remember our ammonium ion? We need to have that memorized. Everything with ammonium is pretty much soluble in water. And then these large oxyanions, so nitrate, okay? Let's see. This is going to be chlorate, or it might be perchlorate. That might be chlorate, and that's acetate. Okay. You can tell they didn't even make me memorize these when I was in college. Or they did, and I just refused to learn. But one way or the other. So those ions. All right. Down here, these compounds are usually soluble. So things that contain fluoride, chloride, bromide, or iodide. Except, our exceptions are silver, lead, and mercury. Okay. So right now, I want you to just focus on learning how to use this table. Silver's really, lead's cool, makes a nice cool color thing. I've got a nice picture of that later. And then silver is interesting. Silver chloride is what they used to do photographic film with. You would expose film with light, and silver would precipitate out. Silver chloride would precipitate out. I doubt film is still done like that. I mean, we barely have film anymore. But, and then sulfate is soluble, except for these with these cations, right? Cations are the positive ones. And then anything that isn't one of these, you just assume isn't soluble. All right? So if I take, let's say I take copper, and I put copper with sulfur, it's not soluble. Copper sulfide, not soluble, because sulfide isn't up here. That's sulfate. Copper sulfite, sulfite's not up here either, right? Copper's not up there, so they're not soluble. All right, so we'll want to use those, and I've got some examples here. So let's go ahead and try these. So using the table, how about ammonium hydroxide? What do you think? I'm just gonna go down and name a list of these, and I want you to get down that list as far as you can using the table. And then I'll walk around and you can ask me questions if you have them. All right, so look over at the table. Try to use the table to do this. All right, spend less time writing down all of them. Write down one, try it. Write down the next one and try it. I always post these notes. Let's go ahead and look at the first one. Okay, maybe let's work through the first two. All right, so ammonium hydroxide, soluble or not soluble? How many people think it's soluble in water? Okay, got a few people think it's soluble in water. How many people think it's not soluble in water? All right, the solubles in water have it. So yes. And the reason it's soluble is if we go over to our table here, it says compounds containing these ions are nearly always soluble. So we're just going to treat them as always. That means there's some exceptions out there that I don't actually know about. Ammonium is always soluble, yes. Okay. How about barium chloride? Soluble or not soluble? How many people think it's soluble in water? How many people think it's not soluble in water? Okay. I think the not solubles have it. I mean, more of you voted for that as well. So I don't have barium up here. That second column is not soluble. And then chlorides. Oh, hold on. What's that say? We come down here. These ions are usually soluble. Chloride. And then our exceptions. Do you see barium in our exceptions? No. Soluble.
It says on the sulfate one, it says barium.
Yeah, but that's for sulfate. Great, good question. I'm glad. Okay, so barium sulfide, yes. Because chlorides are usually soluble unless if you've got one of these exceptions. Okay, does that make sense? Go ahead and work down the next couple, or the rest if you need, if that's where you are. Call me over if you have questions. You can see, so this is once again, I pulled these out of the odd questions at the back of your book in terms of cracking this sort of thing outside. In addition to the homework, there would be, for every odd question, there's an even question that's very similar. All right, and remember that I will pull, half of your last quiz was from the back of the book directly from the odd questions. I'll continue to try to do that. Okay, not all of it necessarily, but a lot. Half of it maybe. All right, so we try two more. Let's look at the next two. So we have iron phosphate. All right. Is iron in any of these things up here? Okay, it's not in things up there. All right, so no iron. Down here, these are anions, so phosphate. Do you see phosphate here? No. Do you see phosphate here? No, so we're down here. Most other ions not soluble. All right? And so we're going to say no. Iron phosphate is not soluble. Let's do red. All right, how about iron 2 chloride? All right, so iron 2 chloride, the formula for that is going to be, that's going to be Fe. It's iron 2, and chloride has a charge of -1, so you still need to be able to do this sort of thing. There's iron 2 chloride. It doesn't really matter for what we do as long as you recognize what the names mean. Is iron up here anywhere? No. Okay, how about chloride? Chloride is right here. My exceptions are, is iron there? So these are mostly soluble. The iron is not an exception, so it soluble? Yes. Shall we do the last two? Okay, we'll do the last two. Lead 2 chloride. Is lead up over here on the right-hand side? We're going to see it on the left-hand side. So chloride. Chloride is right here. Is lead one of our exceptions? Lead 2, in fact, is an exception, so not soluble. Questions on this? Okay. I looked at this and I was wondering whether lead 4 is soluble. Because lead 4 is our other one. I don't know. I've never encountered it. I'd be surprised if it suddenly was, but I'll have to go ask Dr. Hugh since he's the inorganic chemist. He may know. Or I guess I could just ask the internet. All right, aluminum sulfide. Is this sulfide? No, it's sulfate. So aluminum, do you see aluminum up there? I don't see Al up there anywhere. Aluminum's over there in we call it the third column, right? It's not the third column, it's the 13th column, but the third column when you're thinking about top things. So the top rows. So sulfide, aluminum isn't here. How about sulfide, which is S-2, or S2-, I should say. Okay, I don't see that either. So we don't have either of those there. Most other ions are insoluble, so it is no. And insoluble means not soluble. Questions? Okay. So you should be able to use that table. We're going to continue to use the table as we work through the rest of the lecture here. But we're going to use it to predict solubility. Okay. So what I want to do is I'm going to introduce another type of reaction. It's a precipitation reaction. Okay, in precipitation reactions, you combine some things. I'm going to say we combine two solutions because that's really how we're going to present it here. But you combine two solutions and a solid is formed. Okay. And I want to remind you, when I talk about a solution, all the molecules, okay, or ions, are separated from each other and surrounded by water. So a solution in water, and you can have a solution that isn't in water, but that's our focus today. So a solution in water, and in Gen Chem, I think mostly we're gonna always be in water in terms of solutions. In organic chemistry, you may do something else, but a solution in water, all the ions or molecules are surrounded are separated and surrounded by water. And I think we talked about this at the beginning in terms of chemical and physical changes, maybe. I'm pretty sure I talked about it here. You know something's a solution if you can see through it. Okay, so you might have something that's super, super dark in color and you can't see through it, but if you diluted it, you'd be able to see through it. And the way to tell when something's really dilute, so milk is not a solution. Okay, milk has protein molecules that are floating around in it. They're surrounded by kind of fats to help hold them in solution, and that's why you can't see through milk. Okay, and if you dilute, but you could dilute milk to the point where you could see through it, but it would still not be a solution. So what I want to do is, I'm not sure how to spell this actually. If it might be a Y. There it is, a Y. The Tyndall effect. So the way, if you have a solution, always dangerous to just kind of be hitting the internet, right? Usually doesn't bother me. I like this picture. This picture is great. This YouTube thing, we're not going to go to YouTube. But this is the Tyndall effect. So if you take your milk and you dilute it, it looks like something like this, right? Okay, and there you can still see that you can't see through it. But if you diluted it more and more and more to where you could see through it, the way you can tell whether something is a solution or not is you shine the light through, and here you can see this is a solution. It could be just water, it could be salt water, it could be sugar water. It would look like this, and you can't see the laser at all, right? But here you can see the laser because there are particles in that all molecules aren't separate, and they make big enough particles that they bounce the laser light off of it. Does that make sense? Okay. So, and then here, I guess, is an example where you could try this at home with just a flashlight instead of a laser. Can you see the effect here? Okay. So that's the Tyndall effect. That's how, if you don't have, if you have something pretty dilute and you'd be able to see through it anyway, that's how you would tell. All right. So, so a solution, all things separate out. If all the atoms, all the ions and all the molecules separate from each other, you will be able to see through it, unless it is highly colored, in which case you could dilute it, and then you'd still be able to see through it. So let's go ahead and predict this sort of stuff. Actually, I want to give you an example of something that isn't a solution. This is milk of magnesia right here. So you may have heard of this before. Anybody know what this is for? You have an upset stomach, okay? So upset stomach, and that upset stomach is caused by your stomach being too acidic for whatever reason, okay? That you could take some milk of magnesia, and that would actually neutralize some of the acid, all right? Is that a solution? Why not? I see some shaking of the heads. Yeah, because you can't see through it, right? It's obviously thick too, right? Or maybe I just know what it's like. It's thick, but you can't see through it, so it's not a solution. And in fact, milk of magnesia is magnesium hydroxide. Okay, so this is just you guys just haven't had enough upset stomachs. But this stuff, you can just buy it over the counter. It's not like some rare weird thing. And so let's go ahead and bring our table back down here. I'm going to bring our table down, and then I'm going to shrink it down, and we are going to use it over and over and over again today. Would you expect magnesium hydroxide to be soluble? Can you guys see that? That's probably too small, isn't it? All right, I get to bring it down and make it big anyway. All right, so up here, magnesium hydroxide. Do you see magnesium on here anywhere? No. Do you see hydroxide, OH minus, on here anywhere? No. So then we're down on most other ions, all right, not soluble. And so that goes along with what we, not your experience, but what we see in this picture. All right, let's try another one, but let's try an equation for this. So if I put this like that, I'm going to keep our table up there. What if I started writing an equation, okay? And I'm going to make this an ionic equation. Or we'll predict, and then we'll talk about types of equations with it. So let's say I had lead nitrate, lead-2 nitrate. It's going to be solid. I need to figure out what letters to put. Do I put aqueous here? Do I put solid there? Do you guys see nitrate up there anywhere? Yeah, it's right here. Are there any exceptions? No, I'm done. It's soluble, okay? So we've got lead nitrate, okay, plus sodium iodide. Yep, sodium iodide. I'm going to put a 2 in front of it because I'm pre-balancing. Sodium iodide, is it soluble? Yes. Why? Sodium, right. If you look up here, we've got sodium. It's up in this top thing. There are no exceptions. So we don't need to worry about anything else. Right? We can just stop there. How about, so this is a double displacement reaction, right? Remember our double displacement reactions? We swap partners, right? So the iodides are going to go with the leads and the nitrates are going to go with the sodiums. How about lead iodide? So you need to be able to do this, right? How many, what's the charge on lead over here? +2, because it's +2, because nitrate is -1, right? You're supposed to have that memorized, but it's over there if you don't. So we've got 2 of these, so I have to have +2 here to make that neutral. All right, so we've got lead iodide, right? Is lead iodide going to be soluble? No, why?
Lead's an exception.
Lead iodide is one of those things that's soluble, but lead is one of our exceptions, right? And it's also the +2 form of lead. So that's going to be a solid. And then we have sodium nitrate. Is sodium nitrate going to be soluble? Yes. Why? Sodium, right? All sodium compounds are soluble. All nitrate compounds are soluble, right? So that's great. So we've got both of those. So I do a little AQ next to this. And what's left for me to do here to make this all right? I need to balance it by putting a 2, all right? So you got all these things going on, all right? So, I mean, this week, you're going to be expected to balance things going on. So I could ask you to balance equations in the future, and it's not gone. It's not done in terms of quizzes. But our focus on your next homework and your next quiz will be bringing these things together and doing solubility. All right, so that's more important than balancing. Okay, so that's what that looks like. This is the molecular equation. And now what we're going to do is we're going to complicate things up a little bit. And we're going to we're going to make our ionic equations a little more complicated. So we're going to talk about 2 types of ionic equations. The complete ionic equation. Okay, for the complete ionic equation, all ions are shown. right, so I need to go back and break this up. I've got a lead on the left-hand side up above. So now I'm going back up and I'm looking at this to write this. I've got lead nitrate, right? One lead, and it's +2, right? So here you have to figure out what those charges are. It's +2 plus 2NO3 minus, right? Both of these being aqueous, so we'll label them as such. Plus sodium iodide. Whoops, that should be labeled as aqueous. Sodium iodide. 2 sodiums. Aqueous plus 2 iodines. Aqueous or iodides. Aqueous plus, don't forget your charges. All right, and that's going to go ahead and that's going to make a lead iodide, which is a solid. So it all stays together. It's not aqueous. The ions do not break apart because it's solid. And then I'm going to have 2 sodiums for my sodium nitrate on the right up here.
Do we have the
Did I miss something?
Do we have to put the charges with this?
Great question. We need to put the charges here? We don't, because it's broken up. It's not broken up. It is neutral. There are 2 minus charges and a +2 charge here, and they neutralize each other, and it's 1 unit. Does that make sense? Why we don't do that? Okay. So we don't write the charges when it's like that. Great question. Thank you for asking it. And so we've got 2 sodiums, aqueous again, plus 2 nitrates, also aqueous. That is the complete ionic equation. All right? Now we have one more thing we're going to add. This is the most complicated. It is called the net ionic equation. And it only shows kind of where the action is. It shows things that change. So if I look at these ions, before we do it, let's look at these ions up here. What do you see about this nitrate ion? If I look at the left-hand side and the right-hand side, what do you see? Anything interesting? There's a nitrate on the other side, right? Exactly the same. Whoops, that's not my nitrate. I've got 2 nitrates and 2 nitrates, exactly the same. Okay, what about, do you see anything else that's like that? The sodium, right. 2 sodiums, 2 sodiums, right? Exactly the same on both sides. So nothing changed for those. So if I was to make a little key here where I put these 2 underlines, what we call these are spectator ions. Okay, they're just watching, they're not doing anything. All right, so we can talk about the net ionic equation. And the net ionic equation just shows things that don't change. Okay, it does not include the spectator ions. Spectator ions are just watching. They're not doing anything. So if I do the net ionic equation for what we drew above, that's going to be on the left-hand side, I've got lead 2 plus, and it's aqueous, plus I have 2 iodines that are aqueous, iodine minus, and that's going to make lead iodide solid. And that's it. That's the whole net ionic equation. It looks like I balanced it correctly. Any questions on that? Yes, Taylor.
said, the definition says it just shows things that do not change.
It just shows things that change. Thank you. It does not include the spectator ions, which are the things that don't change. Thank you. All right. Questions? Other questions? All right. So here, then, this is actually a picture of that reaction, and it's super pretty. I used to do this as a demo. Turns out, lead, as you probably know, lead is pretty toxic, right? So this is then going to be lead. I'm just going to rewrite it. But it's super short, right? And it's the iodide ions. And this is not, it's not solid lead, it's aqueous lead. You'll never have anything charged that's a solid, okay? At least in this class. So this is what this reaction is. That's what that is. You take two solutions, lead nitrate or lead something acetate. One of those one of the anions that everything's soluble with, and you mix it with sodium iodide, lithium iodide, potassium iodide, one of those things, and you get this beautiful yellow solid that comes out. Okay. Which is lead containing, and it's toxic. And this is well, actually, I don't know why lead was always in paint. It may have been a colorless compound they did it, but they used to put lead in paint because it helped to make things. It may have good physical properties too, but it definitely it gave you that kind of base color. Not this one. Might be lead chloride is colorless or is white, colorless. Yeah. Questions? Okay. All right, so then I have a mess of practice problems for us to work through here. So let's just do a lot of practice problems. So what I want you to do is I'm going to give you two things, and I want you to combine them and complete the reaction. Okay? And we'll use the solubility table for that. So let me go ahead and pull the solubility table down first. Put it over there. This isn't going to leave me a room enough to write these out, but so let's go ahead and do magnesium bromide, which is aqueous, plus lead chlorate. I'm going to say chlorate. I may not actually have that name right because, like I said, I haven't worked with it, and they either didn't make me memorize them or I just took the hit on those points. I didn't memorize them in college. So go ahead and take those and write out. What I want to see is the net ionic equation for those. Okay. So that's the big payoff here. You might need to draw the complete ionic equation. All right. I'll give you this one. I'm going to write a couple more up on the board in case you get done quickly. me questions if you have any. And focus on writing the first one and then trying the first one before you, that's a MGDR2, sorry about that. Focus on working the first one rather than writing them all down, all right? I post these, they're also, once again, these are examples, if you want to look at them, they're the even number problems in the back of your book, that's where I'm pulling these from. Yes?
So the first one being
So, if we look at that, most of these are soluble, right? So you don't put these together, okay? Right? So those things are going to be separated this like and then magnesium is going to be 2 plus, right?
So when you put them which is
They wouldn't be there, I mean, those are over here. What is this item? So you might be best off here, leading it in the molecular weight, right in the food ionic weight.
Let's go ahead and work the first one. I've got some good questions over here, and I want to kind of give you a method for this. And to make myself room, I'm going to need to get this chart out of the way, so let's decide what's insoluble here first. So we're going to swap partners, right? We're going to take this ion with the magnesium. These ClO3s are pretty much soluble with everything, right? So when I switch this, my magnesium chlorate, let's say, is going to be soluble. When I switch the bromine with the lead, bromines are usually, or bromide ions are usually soluble, except with lead, right? So the lead bromide is going to be insoluble. So having done that, let's get this solubility table out of the way here to make me a little more room. So how would I do this? Because I've got to write the net ionic equation, and I probably want to do this in steps. I probably don't want to shortcut it. So I've got these. I'm going to switch partners. I'm going to write the molecular equation first. So I'm going to go magnesium, chlorate, 2, that's aqueous, right? We said that was soluble. And then I'm going to make lead bromide, and that's going to be a solid. All right? So that's the first part of this. Check all my ions. Are things balanced? Yeah, they look balanced. Look okay to you guys? All right, great. So we've got that. So now I'm going to do my complete ionic equation and break everything up so it's easy for me to see my spectator ions. So this first thing, magnesium bromide, is soluble, so it's going to break up into ions. So magnesium plus 2, aqueous plus 2. They don't come off as a Br2, right? They're two, so it's going to be a bromines, 2 bromines, aqueous, right? And then I'm going to have my lead, and that's going to be 2 plus, and that's aqueous, plus 2 chlorates, and that's also aqueous. And then over on the other side, I'm going to have, this thing is aqueous, so it breaks up into its ions. Magnesium 2 aqueous plus 2 chlorates, and that's aqueous, plus, what about this one? It's solid, so it doesn't come apart. So PbBr Br2 solid. Okay, like that. Now, which of these are present the same on each side of the equation?
MG and Cl.
Yeah, so Mg, right, I see that on both sides. And this chlorate I see on both sides, right? And they haven't changed. And then everything else is different. So that was my complete ionic equation we just drew. And these yellow underlined things are spectator ions. So I'm going to remove those spectator ions when I draw my net ionic equation. And so that's going to be lead 2 plus aqueous plus 2Br. And I'm just writing what's left at this point for my net ionic equation. And that's going to make lead bromide solid, like that. That's my net ionic equation. Okay? Try the next one. What I will do is I will label those in a minute. I'm going to hand back your quizzes while you try the next one or more. But I want to give you these solubility rules. And I will also, for the notes, so let's just really quick. This is our net ionic equation. And our complete ionic equation is the one above it. All right, so try that one while I hand stuff back. All right, I'm gonna quick do the answer up here. Alright, so help me out, which of these are soluble when I swap these? Is aluminum phosphate soluble? No, right, phosphates aren't soluble, aluminums also aren't soluble. How about potassium chloride, soluble? Yes, everything with potassium is soluble, right? And then most things with chloride are soluble, but I didn't even need to go down that any farther, right? If I've got one of these things up in the top, I don't even need to do anything else. So I'm going to go ahead and just really quickly, and I'm going to actually, I don't recommend you skip the complete ionic equation unless you're just acing these. I'm going to do it because I have, well, no time. So I'm going to actually, I'm going to write this out. So I've got aluminum and phosphate. Your final answer here should have been aluminum plus 3, right? That's aqueous, plus phosphate, which is 3 minus. You should remember that's one of the ones you need to memorize. Okay. Phosphate goes to make aluminum phosphate solid. That should be your net ionic equation. Okay. I recommend you do the steps we talked about above. I did it quick like that so I could give you the answer. And I will go and in case you did the next one, I will give you the answer for that one as well. I'll write it after class. You guys have a great couple days, and if anybody wants to see me this afternoon, please come talk to me.
Hi, Doug. I would like to visit at some point.
Yeah.
Are you available Tuesday after, say like 1?
I can do Tuesday, right, so I have a 1:10 lab, so I can do like noon. You could come to the lab and I could try to help you. So my lab is up a floor. If you wanted to come, I could like when I don't have somebody talking to me, I could come back and forth and talk to you.
So, okay, wait, I'm only asking for one just because I have a meeting with an orientation leader and I'm
Yeah.
not allowed